what do we mean by enrichment of ores? The processes used for removing the gangue from the ore are based on the differences between the physical or chemical properties of the gangue and the ore. Now, what do we mean by gangue? So these refer to the impurities in the ore. Now these impurities could be things like soil, sand, etc. Now there are many different processes which are used based upon the physical and chemical properties of the impurities and the ore. Like if they differ in their physical properties, we use a different method. If they differ in their chemical properties, we use a different method. Now some of the methods or some of the separation techniques that are often used are hydraulic washing, froth flotation process, magnetic separation and chemical separation. So just to give you a quick understanding, for example, we use hydraulic washing when the ores are heavier than the impurity particles. So in that case, we do this kind of washing. So the ores being heavier, they remain at the bottom, and the impurities being lighter are on the top. Froth flotation process is used specifically for sulfide ores of copper, lead and zinc. Similarly, magnetic separation is used when the impurities are non-magnetic but the ores are magnetic. Now, since they differ in their magnetic properties, therefore we use this magnetic separation method. Chemical separation is used if the chemical properties of the impurities and the ores are different. So they react differently with a particular substance. So that is another way we use to separate the impurities from the ore. Now, when we talk about metal extraction, so before we even talk about the exact process of metal extraction, we talk about grouping of metals. Now, there are three categories of metals that we deal with. First is metals of low reactivity, which is also called as low activity series. That means here we talk about metals which are very unreactive. That is, they do not react much. One such example is an ore of mercury, that is HGS, the sulfide ore of mercury. This is an unreactive ore and therefore it falls under the category of low activity series. So all these ores, they are generally found in their native state. So this is like our first category. The second category is metals of medium reactivity. So they form the medium activity series. So here they are moderately reactive, neither very less reactive nor extremely reactive. So they are like moderately reactive. So they are generally present as sulfides or carbonates in nature, but it is always easier to get the metal from metal oxides rather than sulfides or carbonates. Therefore, for these kind of metals, our aim is always to convert the sulfides or carbonates into oxides, because from metal oxides we can very easily get the metals. So you understood, right? So these metals, they generally exist as sulfides or carbonates, and what is our aim? To convert these sulfides and carbonates into their oxides. Right? So generally here we talk about reduction using carbon. So this is basically this category where zinc, lead, iron, copper falls into. And then we have metals of high reactivity. So here obviously we are talking about metals which are extremely reactive, for example potassium, sodium, calcium and so on. So here carbon doesn't act as a reducing agent. So this is our moderate series, that is medium reactivity series. This is our high activity series. So here these metals are obtained by electrolytic reduction, or what we call as electrolysis. So all that I'm trying to tell you is we will talk about the extraction method of our metals, but there are different processes for these three categories. So therefore we are going to talk about the processes for each of these categories: low reactivity, medium reactivity and high reactivity. So let us start with the low activity series, metals of low reactivity. So these here we generally have these metals are present in the form of their sulfide ores. So let us take an example. Let us take the example of the sulfide ore of mercury. This is an ore of mercury. And what do we do? Now these sulfide ores are converted into the oxides, because you remember I told you that it is always easier to get the metal from its oxide rather than from its sulfide or carbonate. So our first aim is to convert this sulfide ore into an oxide ore, that is HgO. And for that we combine it with oxygen in presence of heat. We heat it with oxygen basically, and that process is called roasting. So roasting is a process wherein we heat it strongly, strong heating in excess of air. So what is roasting? Strong heating in excess of air. So when the sulfide ore undergoes roasting, it forms HgO, which is oxide ore, plus SO2. Now it is very easy to get the metal from the oxide ore. So HgO, when it is heated, it forms Hg plus O2. So this is how we get the metal, and then the metal is refined. Now we will talk about refining of metals later. So now you understood, if it is a low reactivity series, it is generally a sulfide ore. It undergoes roasting, gets converted into its oxide ore. From there it gets converted into the metal, and then the metal is being refined. Now we will talk about metals of medium reactivity. Now most of these metals, they exist either as their sulfide ore or as their carbonate ore. Now if it is a sulfide ore, again the process will be the same. It will undergo roasting, that is strong heating in excess of air, and it will form the oxide ore, that is oxide of metal will be formed. From there it will get reduced to metal, and then the metal will get purified. What if it is a carbonate ore? Now if it is a carbonate ore, then it undergoes a process called calcination. What is calcination? Calcination is strong heating in limited air. So you know what is the difference between calcination and roasting? Roasting happens in excess of air. So roasting always happens in excess of air, and calcination happens in limited air. Let us take an example of a carbonate ore. Let us say we talk about zinc carbonate, ZnCO3. So when we heat it strongly in limited air, so therefore there is no oxygen, it forms ZnO plus CO2. So ZnO is the oxide of zinc. So from ZnO it can be reduced. And how is it reduced? ZnO reacts with carbon, because reduction to metal happens with carbon. So ZnO reacts with carbon to form Zn plus CO. So this is how we get the metal. So first the carbonate is converted into the oxide, and then the oxide is reduced to the metal. So that's like a simple option. Now if it was a sulfide ore, let us suppose if we talk about zinc sulfide, in that case roasting would have taken place. That is ZnS plus O2 in presence of heat. When this is strongly heated, it forms ZnO plus SO2, and then ZnO was again similarly reduced to the metal zinc. So this is how it happens for metals of medium reactivity. Now this reduction of metal from the metal oxide not only happens with carbon, there are other ways also. Now what are those other ways? Let us learn about them. So another alternative method is the displacement reaction. Let us suppose we talk about an ore, talk about the oxide of manganese, MnO2. So if MnO2 reacts with aluminium, because carbon is not only the reducing agent that you can use, there could be other reducing agents like sodium, calcium, or even aluminium. So for example here in this case with MnO2, when it reacts with aluminium, it forms Mn plus Al2O3 plus a lot of heat energy is produced. But the only thing is that in these kind of displacement reactions, they are highly exothermic. That means a lot of heat energy is produced. In fact, so much of heat energy is produced that the metals are produced in molten state. So that's like one major difference. But otherwise, I hope you understood it, right? Initially, these metals, they exist as carbonate or sulfide. If it is a carbonate, it undergoes calcination. If it is a sulfide, it undergoes roasting. At the end of calcination or roasting, we get the oxide of the metal. And then the oxide is reduced to the metal where a reducing agent is used. Most of the times it is carbon, but sometimes it could be other agents like sodium, calcium, or aluminium. So that's about the medium activity series. Let us now talk about metals of high reactivity. So for such metals, the electrolytic reduction is used for the molten ore. So what happens in electrolytic reduction? So in electrolytic reduction, for example, let's talk about sodium. So let's say for the process of electrolysis, you have the electrolyte that is used is NaCl, and then you have the positive and the negative electrode. Right? Now what happens at cathode? So let's talk about cathode, that is the negative electrode. So there Na plus accepts an electron to form Na. So that means the sodium metal is depositing on the cathode. Whereas at the anode, chlorine minus forms chlorine plus 2 electron. So basically, as a part of this electrolytic reduction, we see that the metal is deposited on the cathode, and that's how we obtain the metal. So this is just a reduction technique. Like normally in the previous cases, either for medium reactivity and so on, we used carbon as a reducing agent. But when we are talking about metals which are very reactive, their carbon doesn't act as a reducing agent because these metals have more affinity towards oxygen. So therefore, in order to reduce these metals, we make use of the process of electrolysis. After metal extraction is done, then comes refining of metals. And the most widely used method for refining impure metals is electrolytic refining. So let us look into it in more detail to understand electrolytic refining. From the name only, we understand that here the process of electrolysis takes place. So what happens is we have this setup where the impure metal is the anode. So anode is the impure metal. That means the metal with impurities. And the cathode is the pure metal. So what happens over a period of time? So our expectation is over a period of time, all the pure metal will get collected in the cathode, and that's how we will be able to refine the metal from impurities, right? So as part of this electrolysis, we take solution of the metal salt as electrolyte. For example, if we are talking about the metal copper, so we take copper sulfate solution as the electrolyte. So impure copper on the anode and pure copper gets collected on the cathode. Now when current is passed through the electrolyte, that is through the copper sulfate solution, impure metal from the anode, they dissolve into the electrolyte. So basically the impurities, they dissolve into the electrolyte, and what happens? An equal amount of pure metal from the electrolyte is deposited on the cathode. So it's simple. So as electrolysis takes place, what happens? All this, not only the impurities get into the solution, this entire thing, this entire impure copper gets into the electrolyte. Now out of that, the impurities stay there in the electrolyte, whereas the pure copper gets collected in the cathode. Now, when we talk about the impurities, there could be two categories of impurities. One could be the soluble impurities. So, the soluble impurities will kind of get into the solution. So, they will dissolve into the solution, right? And what happens to the insoluble impurities? They settle down at the anode. So, basically, they settle down here as insoluble impurities. So this is how we separate the impurities, both the soluble as well as the insoluble impurities from the pure metal, and we get the pure metal collected in the cathode. And these impurities, the insoluble ones, are often termed as the anode mud. So in this way, we do electrolytic refining to purify the metals. Basic question: what is required for corrosion? And the answer is both air and water. So note this word, both. So only presence of air or only presence of water is not enough for corrosion. So corrosion takes place only when both air as well as water are present. So we will do a small activity to show that how both of these are required. So let us suppose that you have three test tubes, test tube 1, 2 and 3. So in the first test tube 1, in all these test tubes you have used an iron nail, so where rusting can take place, right? So we have put one iron nail in all these three test tubes. In the first test tube, it is exposed to both air and water. So water is present here and it also has exposure to air. So both are there. So what do we notice over a period of time? We notice that rusting takes place. So rust is formed. So here air and water, it is exposed to both air and water. In the second test tube, we have used distilled water, but there is no air. So that means in this case, we have exposure only to water. And here we observe that no rusting takes place. In the third test tube, there is no water. So basically we have used a dehydrating agent called calcium chloride. So it takes away all the water. So basically here there is no water, only air. And in this case also we see that no rusting takes place. So this clearly shows that for rusting to take place, that is for corrosion to take place, both air and... Learn about galvanization. So galvanization is a method of protecting steel and iron from rusting by coating them with a layer of zinc. So if you put a layer of zinc, you do not see rusting happening even in the presence of water and air. How? So that's the most important question. Now normally what happens is iron loses electron to form the Fe++, right? So iron loses electron to form that positive ion. Now if this electron is taken by oxygen, in that case rust is formed. So for rusting to take place, we need air and water from where we get this oxygen. So if oxygen takes this electron, we see that iron oxide, which is rust, is formed. Now, what do we do when we put a layer of zinc? So what zinc does is, zinc takes away this electron. And therefore, it doesn't allow oxygen to take it, and that is how it doesn't allow rust to form. And for this reason, zinc is often termed as the sacrificial anode, because zinc is sacrificing itself to protect the steel or iron from rusting. So zinc takes this electron and therefore prevents oxygen to take the electron, and therefore rusting doesn't happen. As I said, the zinc is the sacrificial anode and it cathodically protects the exposed steel. Now, something very important here. What do we mean by it cathodically protects the exposed steel? Now, in literal terms, it means that, let us suppose you have, say, an iron article and it is coated with zinc all over. So, quite obvious that it is protected from rusting all over because it has a zinc layer. Now let us suppose that in middle somewhere, because of scratching or something, a little bit of zinc layer is missing. It is not there. That doesn't mean that that particular portion is now, can get rusting. It will still not be rusted. That's because zinc cathodically protects the exposed steel. So even though the steel is exposed or the iron is exposed in that particular area, but still it has that effect of zinc and therefore rusting doesn't take place there. Now there are several ways by which galvanization take place, as in how do we put this coating of zinc on iron. There are two different methods. One is hot dip galvanizing, wherein what we do is iron or steel is dipped in molten zinc. So you have molten zinc and you dip iron or steel into that molten zinc. So that is called hot dip galvanizing, because you dip the metal to get a layer of the zinc. The other method is electroplating. So electroplating is again more like the process of electrolysis, where you have a cathode and an anode. So here you run a current of electricity through the electrolyte, which could be for example, if we are talking about zinc, so it could be a zinc sulfate solution, right? And you have a zinc anode, and you have the other cathode as the other metal, which needs a layer of zinc, right? So in that fashion you get a layering of zinc. For example, if you have zinc as the anode and you have, let's say, steel here, and here you have the electrolyte as ZnSO4. Now when current is passed through the electrolyte, what happens is zinc from the anode gets into the solution, and also it gradually gets into this cathode. So therefore the steel object gets a layering of zinc over a period of time. So that's how we do galvanization. So these are the two ways to prevent corrosion is alloying. So alloying is a very good method to improve properties of a particular metal as well. So what is alloy? It is a homogeneous mixture of two or more metals, or even a metal and a non-metal. Now as I said that by mixing two metals or by mixing a metal and a non-metal, the overall properties of the metals are improved, and that is where corrosion is also prevented. So let us look at few examples. In fact, another property that you would have noticed is the electrical conductivity and the melting point of an alloy is less than that of the pure metals. Let's look at these examples. If you talk about brass, it is an alloy of copper and zinc. Now if you look at the melting point of copper or zinc and compare the melting point of brass with that, you would see that the melting point of brass would be a lot lesser than copper or zinc. Similarly, if you talk about bronze, that is also an alloy of copper and tin. If you talk about solder, that's an alloy of lead and tin. So these are some popular examples of alloy. In fact, you would have seen a lot of brass or bronze artifacts which are often used as decorative items in our houses, right? So these reactions, NaCl solution and copper metal, MgCl2 solution and aluminium metal, FeSO4 solution and silver metal, and AgNO3 solution and copper metal. So let us look at each of these options one by one. So in the first option, sodium and copper. So which is more reactive than whom? So sodium is more reactive than copper. Therefore, copper will not be able to displace sodium from its solution. So this displacement reaction will not take place. MgCl2 and aluminium. So magnesium and aluminium. Which is more reactive out of these two? So magnesium is more reactive than aluminium, and therefore aluminium will not be able to kick out magnesium from its solution. So here also displacement will not take place. FeSO4 and silver. So basically out of iron and silver, which is more reactive? Obviously iron, and therefore again silver will not be will not be able to kick out iron from FeSO4. Then we have silver and copper. So out of these, which is more reactive? So copper is more reactive. Therefore, copper will be able to kick out silver from its solution and take its position. So therefore, displacement will take place here. So copper will form a nitrate and silver will be kicked out of the solution. Right? Now, you may ask, how did I know that who is more reactive than whom? Based on the reactivity series, which we discussed at the beginning of this lesson. Let's look at the next question. Give reasons. Platinum, gold and silver are used to make jewelry. That's an interesting question. We have so many metals, but why specifically are these metals used to make jewelry? That's because they are less reactive. Because most of the other metals, they either react with air, react with water, react with oxygen, right? But these metals, they are very less reactive. They do not corrode. So you do not see anything like a rust or some layer forming on top of them. Besides that, they are also malleable and ductile, because if we want to make ornaments or jewelry, we want the metal to be really flexible so that we can, kind of beat it in the form of a thin wire to form a chain, or in the form to get the designs of a bangle or an earring, right? So the metals need to be malleable and ductile, only then we will be able to make jewelry out of them. And last but not the least, they have very good shine, and therefore the jewelry, they look very good, right? Let's look at the next one. Sodium, potassium and lithium are stored under oil, because sodium, potassium and lithium, they are very, very reactive. They are so very reactive that if they react they react vigorously with air, with water, therefore they are stored in oil. Aluminium is a highly reactive metal, yet it is used to make utensils for cooking. Quite a few advantages with aluminium. For example, first of all, aluminium is lightweight. Now that's important for utensils, right? Not only that, cheap. So if we start having gold or silver utensils, they'll turn out to be extremely expensive, right? So it's cheap. It is good conductor of heat, and that's again the most important criteria for a utensil, because we want to cook food in that. So it has to be a good conductor of heat so that we are able to cook. Besides all of these, with aluminium, once aluminium forms a layer of Al2O3, that is aluminium oxide, it protects aluminium from any further corrosion. So that ways it's not that it will corrode for infinite period of time. So one layer of aluminium oxide will prevent it from any further corrosion. Another interesting question. You must have seen tarnished copper vessels being cleaned with lemon or tamarind juice. Explain why these sour substances are effective in cleaning the vessels. I'm sure many of you would have experienced this in your house, that generally the vessels which are used in our puja purpose, or even in the kitchen, many times we use such copper vessels, and you would have seen your moms cleaning these vessels using lemon or tamarind juice, imli. Right? So why? That's because lemon or tamarind juice, they are acidic in nature, and these acids are able to clean the copper vessels very nicely. But that doesn't answer the question. Why is it that the acid is able to clean the vessel so nicely? In order to understand that, first we will have to understand, why does this vessel get tarnished? As in, this vessel is made up of copper, and copper is a shiny metal. So when you buy a new copper vessel, you would see a very good shine on it, like as you see in the picture here. But over a period of time, as it reacts with carbon dioxide, it forms copper carbonate, which is seen as a green layer on the copper vessels. Just think about it. You must have seen these green patches or green layers over copper vessels once they become old. So this green layer is because of this reaction. Now this copper carbonate is basic in nature. And we have learned that if you have a base and if you want to neutralize the effect of the base, what do you need? Exactly, you need an acid, because an acid and a base, they neutralize each other, and that is the reason we use an acid. So when we use this acid, it neutralizes the effect of the base, and as a result this green layer dissolves, and that's how the vessel gets completely cleaned and it gets back its shine. So that's the reason. The next one. So here we have a big question. So though it's big, but it's very interesting. A man went door to door posing as a goldsmith. So he was not a goldsmith, but he was just pretending to be a goldsmith. He promised to bring back the glitter of old and dull gold ornaments. An unsuspecting lady gave a set of gold bangles to him, which he dipped in a particular solution. The bangles sparkled like new, but their weight was reduced drastically. Right? The lady was upset, but after a futile argument, the man beat a hasty retreat. Can you play the detective to find out the nature of the solution he had used? Quite obvious here. So when the gold bangles were dipped into the solution, the weight reduced. Why? Because some gold was dissolved by the solution. And pretty simple and straightforward. What is that solution that dissolves gold? Aqua regia. Yes. which means royal water. It is a mixture of concentrated hydrochloric acid and concentrated nitric acid in the ratio of 3:1. So concentrated hydrochloric acid and concentrated nitric acid in the ratio of 3:1. So that's aqua regia. So hereafter, if you come across a person like this, always know it beforehand.